Welcome to another lesson on mechatronics. Today's topic is DC motors. We have a beautiful BLDC, which means a brushless DC motor, in front of us. In a few minutes, we will also explore a brushed DC motor. In this video, we will primarily focus into the workings of brushed DC motors, while reserving the discussion on brushless DC motors for a future video. In essence, a motor is a device that converts electrical energy into mechanical energy, which is typically transmitted through a shaft. Every motor consists of a stator and a rotor. While the components associated with the stator remain stationary, the rotor and its connected parts rotate when power is supplied. In the case of the BLDC motor, the coils and electromagnets remain stationary, while the body, which is also known as the bell, rotates. There are permanent magnets within the body, which also rotate. Such motors are known as outrunners. On the other hand, in this brushed DC motor, the outer body and permanent magnets are fixed, while the coils and electromagnets rotate. Such motors are known as in-runners. The fundamental principles of science regarding motors are based on the properties of magnets. A magnet is an object that generates a magnetic field and invisible force that attracts other ferromagnetic materials such as iron, nickel, steel, or cobalt. Each magnet has a north pole and a south pole. In our demonstration, we have a rectangular magnet with the north pole represented by the red color with the letter N, while the south pole is depicted in blue with the letter S. This is a permanent magnet, as its magnetic field cannot be switched off and it remains around the magnet at all times. One important characteristic of magnets is that opposite poles attract each other, meaning the north pole of one magnet will be drawn towards the south pole of another magnet, while similar poles repel each other. If we bring the north pole of one magnet towards the north pole of other magnet, they will repel try to move away from each other. Permanent magnets cannot have their magnetic fields switched off, but it is possible for you to create your own magnets, manipulate their polarity, and switch their magnetic field on or off at will. For instance, if you take a ferromagnetic material like an iron rod, wrap a copper wire around it, and connect the ends of the wire to a battery, the rod will become an electromagnet. Electromagnets lose their magnetic field when the current supply is switched off. Moreover, by changing the direction of the current flow, the north pole of an electromagnet can be converted into a south pole, and south pole into a north pole. That is, you can change the polarity of the electromagnet. With this knowledge of permanent and electromagnets, we can now create DC motors. For example, if we create a hole in the center of our permanent magnet, insert a peg into it, and bring it closer to our electromagnet while continuously changing the polarity of the electromagnet, the permanent magnet will begin spinning. Congratulations! You have just created your own very first DC motor. By adding another electromagnet on the other side of this motor, its efficiency will be significantly improved. However, in this design, you would have to manually change the direction of the current continuously to keep the motor spinning, which is impractical in real-life scenarios. Engineers have devised a brilliant solution to overcome this issue. This brushed DC motor is an example of such a solution, although it has been oversimplified for teaching purposes. Engineers strategically position permanent magnets and electromagnets to create efficient DC motors. In this particular example, the motor employs 4 curved permanent magnets and 3 electromagnets. Unlike the BLDC motor we examined earlier, the permanent magnets and the outer body of this motor remain stationary, while the 3 coils rotate. The north and south poles of curved permanent magnets are side by side and are set at a 90-degree angle to each other. Conversely, the 3 coils are wrapped around 3 arms, acting as electromagnets are positioned at 120-degree angles from one another. Perfect alignment between the north and south poles of all 3 electromagnets and the permanent magnets is practically impossible. For example, if the north pole of one electromagnet is perfectly aligned to the south pole of a permanent magnet, other 2 electromagnets will not be perfectly aligned. This clever arrangement of permanent and electromagnets enables the continuous spinning of the coils when power is supplied. Brushed DC motors have an additional crucial component called a commutator, which is part of the rotor. The electromagnets and their coils are also part of the rotor. As the name suggests, Brushed DC motors incorporate brushes, which remain stationary and ensure that only two coils are connected to the electrical supply at any given time. It's important to note that this motor design is simplistic, created solely for the purpose of explaining the concepts. Additionally, this motor features three commutator plates connected to the rotating rotor components. Each commutator plate is linked to a single electromagnet using a small copper wire. On the upper side of the motor, there is a circular wire ring connected to all three coils. Let's explore the current supply in this motor design. We observe that coil A and coil B are connected to the stationary brushes through the commutator plates, while the two brushes are also connected to the battery. Only two of the three commutator plates come into contact with the brushes at any given moment. Currently, only coil A and coil B are energized, as they have a connection to the battery via the commutator plates and brushes. Coil C, however, is not connected at this time. The flow of current is depicted by the yellow line. Coil A, as the north pole of the electromagnet, is attracted to the south pole of the permanent magnet, trying to align perfectly with it. Once coil A aligns itself with the south pole, coil B will disconnect from the brush, and coil C will connect instead. Coil C will then become the south pole of the electromagnet and will try to move away from the south pole of the permanent magnet. Again, the flow of current is represented by the yellow line. At this moment, coil A and coil C are connected to the power supply. As coil C tries to move away from the south pole of the permanent magnet, coil A loses its connection to the brush, and coil C and coil B will become electromagnets. This cycle continues as long as the brushes remain connected to the power source, resulting in the continuous rotation of the motor's rotary components attached to the shaft. Now, let's reiterate the functionality of the motor with the help of a three-dimensional animated angled view. The brushed DC motor is again in front of us, featuring four curved permanent magnets and three coils that can only turn into electromagnets when current is supplied. The permanent magnets remain stationary, with two north poles and two south poles located opposite to each other. There are two wires, one attached to the positive terminal of the battery which is not shown and another connected to the negative terminal. The other ends of the wires are connected to the two brushes. In this view, the positive terminal is connected to this commutator plate, which, in turn, is connected to a coil via a small wire. When the battery is connected, the current flows from this wire to the brush that is momentarily connected to a commutator plate, which is further connected to a coil. Each turn of the coil carries the current, transforming the corresponding arm into an electromagnet, as long as the commutator plate maintains contact with the brush. The current then passes through the small ring on top to the other coil, which is connected to the negative terminal of the battery through the commutator plate and brush. This completes the circuit as the current travels from the brush, through the wire, and back to the battery. At present, the third coil is not connected, as the rotating commutator plates only make contact with two brushes at any given time. The commutator acts as a mechanical switch, providing or disconnecting the current source depending on its position. In this view, the two connected coils are receiving power. As the coils continue to rotate, this commutator plate detaches from the brush, interrupting the power supply to the associated coil. Meanwhile, the previously disconnected coil becomes energized, turning its corresponding arm into an electromagnet. An insulator underneath prevents a short circuit, forcing the current to follow the desired path from one coil to the other, thereby completing the circuit. The north and south poles of the electromagnets change continuously, with the north pole of each electromagnet attempting to align perfectly with the south pole of the permanent magnet and vice versa. The polarity of the electromagnets changes as the rotation progresses and our motor continues to spin. We hope this video has been helpful, and we look forward to seeing you in the next lesson.